Hello, this is Walker Physics, 4th edition, and we are in Chapter 7 on work and kinetic energy. This is the end of the chapter, question number 24. A 0.14 kilogram pine cone falls 16 meters to the ground, where it lands with a speed of 13 meters per second. With what speed would the pine cone have landed if there had been no air resistance? Did air resistance do positive work, negative work, or zero work on the pine cone? All right, well, we know that you've got two different kinds of energy here. Remember, kinetic energy is 1/2 mv squared. Potential energy, which has to do with how high you are in a gravity field and your weight, is equal to mgh. Okay, so the mass times gravity times the height. So whatever the gravitational pull on a mass, which is weight, so the weight is the force falling at a height. That's how much, like if it's up in the air, okay, then it can do some damage if it falls. So the kinetic energy and the potential energy are constant here. It's a conservation of energy. So let's see what we got. We've got a mass here, 0.4 kilograms, 0.14. We've got a distance, 16 meters. All right, so let's find the potential energy first. Normally you find potential energy because it's not moving, and then when it starts moving, it has a velocity, and the kinetic energy is based upon its velocity, and the farther it falls, the faster it goes, okay? Well, we know that mgh is going to be mass, 0.14, times 9.81, times the height of 16, okay, which gives me 21.97 joules. So that's the potential energy. And the potential energy and the kinetic energy have to be the same. The kinetic energy is the energy due to its speed that's falling from that height. So whatever energy it had stored in the potential is what it has as it's showing itself, okay? All right, we know that it is going a final speed of 13 meters per second, okay? So we know that the kinetic energy, or 1/2 mv squared, equals 1/2 times m, and what are we asked to do? What speed would it have the pine cone, with what speed would the pine cone have landed if there had been no air resistance? The air resistance, remember, is slowing it down. The air is in the way and it's plowing through the air molecules, and the air molecules are shoving up and its force is shoving down, and so there's a slowing. So if there's no slowing, then really all I want to do is solve for velocity. So if I know that 1/2 times mv squared equals the same amount as before, okay, so we're going to say that kinetic energy and potential energy are equal to each other. Well, here's my potential energy, 21.97 joules, and it's going to equal 1/2 times 0.14 times the square of velocity. So we'll get velocity by itself. So multiply the 21.97 times 2 and then divide by 14. All I'm doing is getting v by itself. So we'll have 21.97 times 2 divided by 14 equals v squared. And then we want v as being the square root of that. All right, so 21.97 times 2 divided by 14.14. Okay, now take the square root, and I get v equals 17.7 meters per second. And we're looking for significant figures. There's 2, there's 2, there's 2. Okay, so this is going to be 18 meters per second would be its speed. Okay. All right, so 18 meters per second is what it would have been. And it made it with 13 meters per second. Okay, so here's the force. Okay, here was the force. It ended up going in the same direction as the displacement. The displacement's going down, the force is going down, so there is positive work doing it, but it said, did air resistance do positive work, negative work, or zero? The air resistance isn't pushing it down, the weight is pushing it down. The air resistance is actually moving in the other direction. So if the air resistance is a force acting backwards to the displacement, then it must be negative work. It did negative work. So why? It's because the pinecone moved down. It had a force, that was its weight, moving down, but the air resistance was trying to keep it from going down. So air resistance was working up instead of down, and since it was opposite the displacement, then it had to be negative work.